top-class problem solver. The goal of this video is to help us learn to analyze the problem and communicate our solution effectively. A particle is released at time t is equal to 0 from rest at a position y is equal to 3d, where d is greater than 0, and undergoes simple harmonic motion along the y-axis about the origin. At some time later, the particle is at position d and has a speed v. What is the particle's equation of motion, y of t, in cosine form? The problem-solving method consists of 3 steps. The first step is interpretation of the problem. Then we devise a strategy, and then we execute our strategy. The first step of the interpretation is to identify the concept embedded in the problem. The fundamental physical concept in this problem is simple harmonic motion. So in our solution, we write, this is a simple harmonic motion problem. The next step of the interpretation is to create the model and represent the model in a diagram. The physical system of this problem is a particle whose motion is described as being along the y-axis centered on the origin. So in our solution, we draw the motion of the particle as being expressed along the y-axis between 2 points, P max and P min. The fundamental parameters of this simple harmonic motion will be A, omega, and phi. The third step of the interpretation is to extract the data carefully from the problem. In this problem, we are told that the particle is released at time t is equal to 0 from rest, and from this given position y is equal to 3d. We are also told that at some time later, it has a position of d and a speed of v. Notice that our known parameters are expressed in algebraic form. So therefore, our final answer will be expressed in terms of these known parameters, namely d and v. Let us interpret this information as we write it down in the data. First, we are told that it is released from rest. So therefore, its initial position is either its maximum or its minimum. As we are told that d is greater than 0, we know that its initial position is its maximum position. It therefore means that the corresponding position, 3d, is in fact the amplitude of the oscillation. Next, we are told that it is released from its maximum position. This means that its phase at the time of release is 0 in the cosine form. If we're not sure of this, please refer back to the auxiliary circle. Now we are told in addition that this is at time t is equal to 0. It means that therefore this phase is at time t is equal to 0. And we know that the phase at time t is equal to 0 is in fact the phase constant for the entire simple harmonic motion. We can therefore immediately write down that the phase constant for the simple harmonic motion is equal to 0. Finally, we are given information at some unspecified later time. Let us call that time t1. So therefore, we will say that the position at that time is y1, which is equal to d, and its velocity at that time, v1, is plus or minus v. Notice we are not given the direction of the velocity, so we should retain the plus and minus sign. The first step of the strategy is to determine precisely what is required. In this problem, we are required to find the equation of motion y of t in cosine form. So this is what we write in our solution. The second step of the strategy is to construct the concept map. The concept map relates the parameters that are given in the problem and the required parameter. We are required to find y of t. Y of t is given by the amplitude, the angular frequency, and the phase constant. In our interpretation, we have already obtained the amplitude and the phase constant. We are therefore left to find the angular frequency. In this problem, the angular frequency can be obtained by y and v at our time t1. The third step of the strategy is to create an action plan based on the concept map. So moving from our knowns towards our unknown, we start by using y1 and v1 to calculate omega. Our second step then is using omega, a, and phi to write down y of t. The first step of the execution is to follow the steps of the action plan. The first step is to determine omega from y1 and v1. We will use the equation that can be obtained from conservation of energy. It is a good idea with simple harmonic motion problems to avoid solving for time. This is because simple harmonic motion is a time-repeating function, so any solution for time cannot be uniquely determined. We get that omega is equal to v over d multiplied by 1 over 4 times root 2. Notice that it's always good to show a little bit of mathematical sophistication to express your answer in conventional mathematical form. The second step of the execution is to write down y of t in terms of our parameters a, omega, and phi. We use the cosine form of the simple harmonic motion equation. The second step of the execution is simply to write down and highlight your final answer. We therefore write down our final answer and highlight it. The third step of the execution is to check your answer. When you check your answer, make sure that you state clearly what is required, that you give the appropriate unit, and that the magnitude of your answer is reasonable. So first we verify that we have written as our answer exactly what it is that was required. Then we check our unit. In this case, we check our unit by writing in the appropriate SI unit for each of our known parameters. Since the unit of V is meters per second and the unit of D is meters, V over D will be in per second. When I multiply that by T, which is in seconds, I will get a dimensionless quantity. So I will have the cosine of a dimensionless quantity, which in itself is dimensionless. We are therefore left with 3D, where D is in meters, so my overall unit for Y, position, is indeed meters. There are several ways to check the magnitude of our solution. Here's one of them. When we refer to the auxiliary circle, we see that when it is at a position of 1/3 of its amplitude, its velocity v is close to, but not quite equal to, its maximum velocity Vmax. So we can perform this check. Vmax is equal to a times omega. When we substitute our values for a and omega from the equation above, we obtain the following value for Vmax. So once more we see that the velocity v is close to but not quite equal to Vmax. This is our complete solution. Top class. Here once more are the 3 steps of our problem-solving method. Thank you for watching.
Some people